Good morning from Rocket Lab Launch Complex 1, where our Electron rocket is vertical and ready on the pad as we begin the countdown to today's launch. Thanks for joining us for our 47th launch and our 5th mission of the year, scheduled for liftoff at 10:14 local time or 22:14 UTC. In America, that is 18:14 Eastern and 15:14 Pacific. Today we are launching 2 satellites for 2 customers on a mission we have called Beginning of the Swarm, or BTS for our K-pop fans. The primary payload onboard Electron is the NEOSAT 1 for the Korea Advanced Institute of Science and Technology, otherwise called KAIST. And sharing the ride is the Advanced Composite Solar Sail System for NASA. My name is Muriel Baker, Communications Manager for Rocket Lab.
And I'm Kim Thompson, Structural Analyst for Neutron. I'm thrilled to be joining you for today's launch from LC1. We have a bit of an unusual flight path today for this mission. While rideshare missions on other rockets will deliver its entire payload to just one orbit, the 2 satellites on Electron are heading to 2 completely different orbits to each other that are also equal distance apart. NEOSAT 1 is first up for payload deployment to 520 kilometres before NASA's payload heads all the way up to 1,000 kilometres in altitude. Our capability to meet the orbital requirements for two very different missions comes down to Electron's third stage, or what we call the kick stage. Once Electron reaches space and separates the kick stage with the satellites attached to it, it's over to this rocket within a rocket to carry on the mission to those two orbits.
The first time we light Curie, it will be a circularization burn into a 520 by 520 kilometre orbit. Now, once that burn is complete and NEOSAT 1 is deployed, the engine will light up again to increase its altitude to 1,000 kilometres. This highest position on an orbital path is called the apogee, and to be in a circular orbit, both the apogee and its lowest point, called the perigee, need to be the same distance above Earth. Though the kick stage's apogee will have risen, its perigee will still be set at 520 kilometres. So, the stage will need to light its engine again for a third time to circularise at 1,000 kilometres ahead of deploying NASA's Advanced Composite Solar Sail System payload.
Once that's done, the ride's not over. The kick stage will ignite its Curie engine again for a fourth and final time to perform an orbit lowering manoeuvre and bring the kick stage closer to Earth. We do this to help speed up the stage's eventual deorbit, all in support of a more sustainable space environment and limiting space junk where we can. We've completed similar orbit raises, inclination changes, and orbit lowerings across other Electron missions before. Most recently, we went all the way back down to Earth with our successful spacecraft re-entry for Varda in February this year.
Now, some of you may have picked up on the fact that Electron is sporting the usual red and silver colouring of a mission marked for recovery. However, today is not a surprise recovery mission. We just regularly manufacture recovery-ready boosters in the Electron production line, and it just so happened that this booster lined up with this mission. Now on to the satellites on board Electron today. The primary payload on today's mission is NEOSAT 1, an Earth observation satellite that is part of a joint program from South Korea. Led by the Korea Advanced Institute of Science and Technology, NEOSAT's primary mission is focused on the Korean Peninsula and its maritime areas, and it will pair the satellite's data with artificial intelligence to monitor for natural disasters. Other organisations involved with NEOSAT include the Satellite Technology Research Centre at KAIST, the SATREC Initiative, which manufactured NEOSAT, and the Korea Aerospace Research Institute, which is managing the mission's ground segments and technology supervision for the NEOSAT program. NEOSAT is funded by the Korean government's Ministry of Science and ICT. And here's an animation of the NEOSAT mission.
A very exciting time for the Ministry of Science and ICT in Korea.
And to all operators, LDO mission code, just a reminder, we are currently at T-minus 12 minutes and holding.
A quick update from Mission Control there. The launch director has called a hold at T-minus 12 minutes while the team works a ground system issue. Now, the good news is we have some buffer in this window, so we can comfortably sit here while the team works through it. We'll stand by, though, for an update from the operators.
If you're just tuning in, we're currently sitting at T-minus 12 minutes in a hold while the team works through a ground system issue. While we wait for an updated T0, we are being treated to beautiful views of Electron on Pad B at Launch Complex 1 in New Zealand. In fact, it's such a clear day that you can spot the Wairau coastline in the background there.
As you can see from the clock at the top left, the launch director has called a hold at T-minus 12 minutes while we work through a ground systems issue. Now, of course, if we do need to stand down from today's launch attempt, the good news is that we have plenty of backup opportunities in the coming days. So we'll keep listening into mission control, but keep our fingers crossed that we get to watch our 47th Electron lift off shortly.
And to all operators, LT on mission code. We have resumed the count and we are currently at T-minus 11 minutes 35 seconds and counting. Please prepare yourself for go no-go call.
Yep.
Stage.
Yeah. Stage is go.
Avionics.
Avionics is go.
GNC.
GNC is go.
Recon.
Recon's go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
RF.
RF is go.
MM.
MM is go.
LD sub.
LD sub is go.
We're currently T-minus 10 minutes and 50 seconds and counting. We go for the terminal count order sequence at T-minus 10 minutes. From this time, the 3-word hold procedure is in effect.
Okay, great. That was the go, no-go poll completed there, and the team is cleared and ready to proceed with launch. Liftoff is now set for 10:32 a.m. local time, now in under 10 minutes, 20 seconds and counting.
Now, as we mentioned earlier, there's a secondary payload on this mission, deploying much higher, the Advanced Composite Solar Sail System for NASA. This mission is a test of solar sail technology, where a sail that's about the size of a small apartment will deploy from the CubeSat, which is about the size of a toaster. Solar sails use the power of sunlight for spacecraft propulsion, and the objective for this mission is to test how well solar sailing works with carbon fibre sail booms instead of traditional metal ones. It's the first test of this technology in space, and if it's successful, it could pave the way for future solar sail missions to use even larger sails to maximise spacecraft travel. Here's more on the mission from NASA.
A NASA mission is testing revolutionary technology to allow robotic spacecraft to sail on sunlight. The Advanced Composite Solar Sail System introduces a new way to explore the cosmos. Much like a sailboat is propelled by wind, a solar sail spacecraft is pushed by light from the sun. Sunlight is composed of particles called photons. As these particles bounce off the reflective sail, the spacecraft accelerates. This eliminates the need for rocket propellant and makes it possible for spacecraft to travel indefinitely. The sail is stored inside a spacecraft about the size of a microwave oven. Lightweight carbon fiber booms unroll from the spacecraft to form rigid tubes that support the ultra-thin reflective polymer sail. When fully deployed, the sail forms a square that is 33 by 33 feet, or about half the size of a tennis court. Altitude and position are changed by angling the sail toward or away from the sun. Results from the mission will guide the design of next-generation solar sail spacecraft to explore and conduct science across the solar system.
It's exciting to think that the technology tested on this mission could one day be in use for future NASA missions. Some of the potential use cases that could include solar sailing are space weather early warning satellites, asteroid and other reconnaissance spacecraft, and missions to observe the polar regions of the Sun.
Check sequence 57 complete.
Copy, thank you.
In under 7 minutes' time, the Electron rocket you see on your screen is scheduled to lift off from Pad B at Launch Complex 1 with KAIST and NASA's payload. It's launching on a southern trajectory at a 97-degree inclination, first to a 520-kilometre orbit and then onto a 1,000-kilometre orbit.
Right now, the team is loading the rocket's liquid oxygen propellant into both Electron's first stage and second stage, having already completed kerosene propellant loading earlier in the countdown. You can see the white bands on the rocket there. That's where the liquid oxygen has caused moisture from the atmosphere on the outside of Electron to freeze. The propellant for the Curie engine within Electron's kick stage, which sits inside the rocket's nose cone, has already been loaded before the two fairing halves were closed to surround and protect the kick stage and its payloads through launch.
At the bottom of the rocket are 9 Rutherford engines, each of them 3D printed and electrically powered by batteries that drive their propellant pumps. Using electricity and batteries as a power source for those pumps cuts down on the weight and complexity that would have been added to the engines if the Rutherford had been designed to use a traditional gas turbine system. There is a 10th Rutherford engine that powers the second stage, and the main difference of this engine to the 9 on the first stage is the size of the nozzle, which is larger for the second stage version so that it can maximize performance when traveling through the vacuum of space. Otherwise, the 10th Rutherford uses the same batteries and 3D printed components as the first stage engines, including a 3D printed combustion chamber, injectors, pumps, and main propellant valves.
All right, as we look at the clock, we are 5 minutes and 10 seconds left in the countdown to liftoff. Launch operators are currently in control, but once they switch Electron to internal power at T-minus 2 minutes, the rocket's flight computer will autonomously run through the remaining steps. These include the final propellant load of liquid oxygen at around T-minus 1 minute 30 seconds. The call across the nets for that will be that the LOX system is in recirculation, which means that LOX loading is complete on Electron. 30 seconds later, operators will confirm that the rocket's first and second stages are fully pressurized for launch. Then it's through to T-minus 10 seconds when our launch director will begin the countdown to liftoff. We're going to hand it over now to Mission Control to listen in on those calls.
LD GC mission.
GCLD.
ECS disabled, pad auto sequences armed, pad ready for launch.
Copy, thank you. To all operators, LD mission code. From now on, there should be no red flags on your critical LCCs. Recon LD mission code.
LD Recon.
Lock the auto sequence and confirm.
Auto sequence is locked.
Recon, please confirm all expected primary flight computer ASCIIs are green.
Confirmed.
We go for auto sequence start at T-minus 2 minutes. LDs go for launch.
Vehicle is fully on internal power. AFTS is green and enabled for flight.
LOX load complete. System is in recirculation.
Anti-geysering is disabled.
Stage 1 and Stage 2 tanks are pressed for flight.
High flow engine purge enabled.
Yeah, T-minus and 20 seconds and counting. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff.
Safety launch pad.
Begin pitch over.
Stage 1 propulsion is nominal.
The beginning of the swarm has begun its ride to space with that clean Electron liftoff from LC-1. Electron's trajectory will take it up and over the South Pacific Ocean as it heads away from the launch pad. Our first mission milestone will be max Q, otherwise known as maximum aerodynamic pressure, which is the moment where Electron experiences the most amount of stress as it climbs through the atmosphere. We're coming up on that moment now and expecting to hear the call for max Q shortly.
Heat-free battery discharge nominal.
Cleared max Q.
That is Electron clear through max Q, with the rocket now at 15 kilometers in altitude and moving at over 2,200 kilometers an hour.
Next up, Electron will perform 3 actions that are only seconds apart. The first is called MECO, or main engine cutoff, and this is when the 9 engines that you can see glowing at the bottom of the rocket there shut off in preparation for the second step, and that move is called out as stage separation, when the first stage of Electron separates from its second and falls back to Earth. Now the third call out after separation should be second stage engine ignition, when the single vacuum optimized Rutherford engine fires up to maintain the mission's course to low Earth orbit. Now those 3 events are approaching fast, so we'll bring up the audio channels from mission control now.
"15 seconds to staging.
Entered burnout detect mode.
MECO confirmed. Stage 2 ignition confirmed.
Stage separation successful.
There we go, that was MECO, stage separation and engine start on the second stage. We have had a nice clean camera feed of those things happening, with the camera view now held on the second stage engine as it powers the mission on. Beginning of the swarm is now over 100 kilometers above Earth, past the Kármán line, and moving at more than 8,000 kilometers an hour. The next mission milestone is fairing jettison, or separation of the nose cone, and that's what protects NEOSAT 1.
As you just saw, fairing jettison is now complete. We dropped those two fairing halves early into the mission because they're not needed for satellite protection anymore now that we're through Earth's atmosphere. That dead weight is gone, and the mission is now a step closer to our first payload deployment at 520 kilometers.
We have a couple of minutes to go until our next mission milestone, and that will be the battery hot swap on the second stage, currently expected to take place at the T+6 minutes 20 second mark. Right now, though, Electron's second stage is continuing along nicely to our target apogee of 520 kilometers for our first payload deployment for KAIST. This KAIST satellite is the first of up to 11 satellites planned by them, which will help to increase the program's observation rates of once every 2 to 3 days to 3 to 4 times daily.
It's T+4 minutes into the mission. Electron is still progressing smoothly through flight, and all remains healthy with KAIST and NASA's satellites. For NASA's payload, packed into this small satellite, are Composite emerge from its cocoon. This satellite will test how the pressure of sunlight pushing against its sails moves the satellite around. The closer to the sun, the better to test its solar sail technology, hence the reason for this mission requirement of a much higher orbit than the primary payload on Electron today.
Throttling down.
T+5 minutes 32 seconds, and our launch operator's next call out will be for the battery hot swap. Our rocket engine's pump is battery powered, and since it's been flying for a while now, its power source is starting to run low. So, to keep the engine and the mission going, Electron's engine power system swaps to a new battery pack for fresh and continuous energy supply to the electric pumps. The old set of batteries will be discarded, which you can sometimes see on the screen as it happens. So let's listen into mission control for that call.
Hot swap successful.
And as confirmed by Mission Control, battery hot swap has been completed for the second stage Rutherford engine. Propulsion remains nominal, and the mission is continuing on its journey to that first payload deployment with KAIST and NEOSAT 1. Now, of course, once NEOSAT 1 is deployed, that is only the first of 2 satellites to be released on this mission. Electron is also carrying NASA's Advanced Composite Solar Sail System satellite that will be deployed at twice the altitude we're heading to now, from 520 kilometres above Earth to 1,000. To do that, we'll first need to repeat the stage separation process we completed earlier in the mission, this time separating Electron's third stage, or kick stage, from the second stage that's currently firing hot on your screen. That second engine cut-off milestone, which you'll hear called out at SECO, is expected at around 9 minutes into the mission.
T plus 7 minutes 47 seconds into the flight, and the mission is continuing nominally. If you take a glance over at the right of your screen, you'll see some telemetry from Electron's second stage, showing us that we have about 16% of propellant remaining. We're currently cruising along at a speed of over 21,000 kilometers an hour and approaching an altitude of almost 209.
We're coming up now to engine cutoff on the second stage, the last action this stage will perform for the mission. Much like with the first stage, Electron will power down the Rutherford engine on the second stage to allow the kick stage to separate cleanly. We time the engine shutdown for right as we reach that target perigee of 250 kilometers. Let's listen out for that engine shutdown and stage separation now.
Seeker confirmed.
Stage 3 separation confirmed.
A great call from Mission Control. The second stage engine has turned cold and the kick stage has separated, ready to begin the payload deployment process. Now, this mission, of course, is a little different to a regular Electron mission, so here is a reminder of how today's two deployments will work. Now that the kick stage has been released, it will now go into a phasing orbit of Earth. Because it's been set into an elliptical orbit from its perigee, it needs to head around to the other side of the planet to an apogee of 520 kilometers before it fires up the Curie engine to course correct into a circular orbit. Now, once it does, NEOSAT 1 will be deployed to begin its mission for KAIST, and that will be phase 1 for the kick stage.
Phase 2 will see it light up its engine again to perform an apogee raise to 1,000 kilometers, the target altitude for NASA's satellite. That apogee raise will bring the kick stage out of a circular orbit and back into another elliptical one. Here, the kick stage will do another half pass of Earth before the dots reconnect again at 1,000 kilometers, where it will light up its Curie engine for a third time to circularize its orbit before payload deployment.
Once that's done, it will be on to phase 3. The Curie engine will ignite a fourth and final time to undo its circularization and bring it back into an elliptical orbit. This orbit lowering maneuver will help to speed up the kick stage's deorbit, doing our best to keep space as tidy as possible. For now, though, we will leave you with a graphic of Electron's coast phase ahead of that first Curie ignition, and we'll come back to this webcast to listen in for confirmation of that first payload deployment at around T plus 45 minutes. So we'll see you back here then.
Curie catalyst heater scheduled to enable.
Approximately 5 minutes to AOS at Spain.
Welcome back to the webcast of Rocket Lab's 47th Electron mission. We're here for the deployment of Electron's first payload on this mission, the NEOSAT-1 satellite for the Satellite Technology Research Centre at the Korea Advanced Institute of Science and Technology. If you're just joining us, we had a successful liftoff of Electron at 10:32 local time, successfully ran through all our mission milestones, and now we're awaiting the first Curie ignition ahead of payload deployment.
We actually have two payloads on this mission, NEOSAT-1 and the Advanced Composite Solar Sail System by NASA, being deployed to two different orbits today. After NEOSAT-1's deployment, Electron's kick stage will ferry NASA's payload to a 1,000-kilometre circular orbit, almost twice the distance for the orbit for NEOSAT-1, which is about to be deployed. Now, since the kick stage's release from Electron about 40 minutes ago, it has since completed its first pass of Earth, and we are now moments away from that first ignition. So let's listen in.
All right, we have just heard that we've had the first of 4 Curie ignitions of the small but mighty Curie engine. This burn will last about 2 minutes, setting us on a circular orbit at 520 kilometres in preparation for KAIST's reference to the Curie engine. But just how small are we talking? Well, it's right here. This engine powers our kick stage and gives us the flexibility to deploy satellites in a variety of inclinations and orbits depending on our customer requirements.
Much like our Rutherford engines, the Curie leverages the rapid manufacture capability of 3D printing. It was first launched on our second mission called Still Testing, and since then we have carried a variation of the Curie engine on all but one mission, our suborbital HASTE mission out of Launch Complex 2 last year. Since hypersonic test launches like those don't have any orbital parameters, our suborbital missions don't need a Curie engine.
There are 3 variations of the Curie engine. We have a monopropellant version, a bipropellant version, and of course, our most complex version yet, the Hypercurie, which saw us take a satellite all the way to the moon for NASA back in 2022. The standard biprop Curie also powers our LEO satellites, like the bus we manufactured and operated to support VADA's in-space pharmaceutical manufacturing and re-entry capsule.
Expected payload deployment.
Fantastic news there from Mission Control. NEOSAT 1 has been deployed. Congratulations to KAIST and its mission partners at the SATREC Initiative, KARI, and the Ministry of Science and ICT. And all the best with NEOSAT's operations starting from right now.
The kick stage's journey is far from over though. In the next 3 minutes, it will light up its engine again to raise our apogee and carry NASA's payload to its target 1,000 kilometre altitude. With about an hour until the Advanced Composite Solar Sail System's expected deployment, we'll be ending the broadcast here. But we'll be sure to share with you confirmation of the payload's deployment across our website and social media channels. So check us out there for updates on the kick stage and deployment of NASA's payload.
Thank you so much for joining us for today's mission. This is Rocket Lab Mission Control signing off.